let's just, this is the next section, 7.5 is just a simple model to show how you get the dielectric current epsilon depends on omega, and what the form, a basic form, and then the property of the basic form. So basically, you're considering that you have a medium, you have molecules, so you have and within this molecule, you have different components. So they are like oscillator with some frequency omega sub j, and they can have damping gamma sub j. And then you have many of them is sum over j, right? And there's a ratio that the total charge is z, the z times e, the electron charge, and then we have different kind of oscillators. So each one has a number f. So you have sum over f sub j, sum over j. So you have f sub j number of this j kind of oscillator, and each have f sub j times e charge. The total charge is z. Right. So these are just the notation of the model. So the equation of motion of the each of these oscillators is just a simple Newton's second law. So your m x double dot. This is acceleration, and then there's a damping term. The damping term, if you put in the right hand side, is minus. Put it in the left hand side, gamma. And this is for one of these oscillators, and usually it's proportional to velocity, right? And then the oscillation, intrinsic oscillation, is a restoring force. So you have omega sub 0 for one of these oscillators. So later we'll change the omega j for the j kind of oscillator. And the restoring force is proportional to x, right? And now if you have a wave propagate through this oscillator with electric field E, right? Then this is and this is changed to minus E and E, right? This is considered just one charge, right? With omega, so just E, but later on we sum over all the charges, right? And the solution for this one is quite straightforward because everything is proportional to E minus I. The wave is proportional to I. So all the dots just change to minus I omega. So you have omega. This has become minus omega squared, and this becomes just I minus I gamma omega. This is omega c. Okay, and then the x will be just equals to just divide everything. So divide everything. And you can change the sign. Comes omega squared plus I gamma omega minus omega c squared. Right. This is just for one charge, and you can multiply by another charge, and that becomes the dipole moment, right? So this is dipole moment, but you multiply negatively, you can consider an electron. This is minus. There's a minus cancel, multiplied by another minus. I'm missing a minus sign. See it again? Oh yeah, that's the equation in the Jackson is minus, so that's fine. That's fine. Yeah. So this is P, the dipole moment. And then you sum over all the contribution of all charges. So, because the polarization is sum over the density, you have a density N, and sum over all the P, sum over all the P. So, because the polarization is the dipole density, so it becomes a, so it goes to N. Minus N. Yeah, almost over the N. You have each one of them has E squared, but then you sum over all the F. Actually, sum over J, the F. So J, each one has a each one has the different damping and different oscillation rate. Right. This is polarization. So remember that the D is epsilon E, right? It's E equals epsilon 0 E plus P, right? So this P going into here is also, that's actually proportional E, and then you have an E here. Right? So epsilon is given by epsilon 0 plus this one divided by E. Right? I mean, actually, whatever the coefficient in front of E. And then, so you can now solve for that. So epsilon is epsilon 0 plus, I think Jackson changed the sign, by changing the sign of the denominator plus N E square over epsilon. I mean, it divided by epsilon, so we don't have to, or we can follow Jackson divided by epsilon. So this is 1. This is epsilon 0. I forgot to divide it by M. There's also M. And M sub J, sum over J, X, J, and change that to a negative of this. Minus I omega times J. So that is how you derive the dielectric constant. That depends on frequency. So you have omega here, omega here. Okay, that's so the derivation is straightforward. One last terminology is that this one is usually we define that as possible frequency square. This is omega p squared. That's something divide this, or maybe it is later on. Oh no, that's actually that it defined it later. Actually, you need to sum over the charge here, so you have a z here. So you need a z here to define. We'll define the possible frequency, but our time, so we later on. Next time we'll finish that discussion, which is needed for the homework question, and related to that, to especially in the low frequency limit, to the. So like this without C is here. So sum over all the F is C. The C is number of charge. So we just consider that could. I mean, Jackson just make it more complicated, more general, with different kind of molecule may have different kind of oscillatory frequency, and they have different density. So there's a different fraction. They add up to be the total charge in this molecule. right? And then so we introduce this F, but at the high frequency limit, then you can just sum over all the F and get a Z out, and that will be you can define that as possible frequency at that point, but not not why not why not you just keep it like okay, but we'll finish that. That will give you the information for the next homework, but we'll get it done on Monday. We just I think we wrote down 7.551, but we need to look at the once we have that, we can look at the property. What this epsilon is about mathematically. What this epsilon, so this is a model. Epsilon now is a function of frequency omega. So 1 plus n. N is the density of the molecule, how many molecule, and each molecule has total charge is Z times E, the electron charge, and it distributed over different kinds of atoms, supposedly. So the J, some over J, each one has F sub J times E charge. So you sum over F sub J is C, so that's 7.52. But anyway, these are just Jackson trying to make it more general. So that's the more general case, you add the molecule can have many different kind of atoms and have so they have different kind of intrinsic frequency. So each atom or charges you can model that as some kind of damped oscillator. So the intrinsic, of course, these are all classical models. In quantum, of course, that's not true. So this electron got driving by the wave, they oscillate, but you have intrinsic oscillation frequency for different kind. So F sub J, like atoms, intrinsic frequency omega sub J square minus omega square minus I omega gamma sub J. Gamma sub J is the damping frequency. Okay, so it still has the dimension of the frequency. If you look at the gamma, the dimension of gamma is the same as frequency, but it just means it's damping at like a damping rate. Okay. So that's what we stopped last time. So this is a model, of course, is simplified, but it's just to give us some physics that generally what can happen. So you can look at the property of this dielectric constant in different limits. First, you can look at when omega is small, so in the low frequency limit, so you can plot that. Jackson has this figure, 7.8, although it's schematic, so you have omega when when omega is 0, you can set the zero. This is 0. This is 0. Then now it depends on whether omega sub j, all the omega sub j's are non-zero or not. If they are all non-zero, then this will be finite. So it's tends to 0. So it tends to just 1 plus. So basically get rid of these two terms, right? Square. Sum of j plus square. Right. So this is just a constant. You can see define a term. I think Jackson would call it something like epsilon background. So when it's just like going back to electrostatic. omega goes to zero, there's no time dependence, so everything becomes electrostatic. But this is the familiar object that we learned from chapter 4. This is the dielectric constant for electrostatic. So you have epsilon sub b, you put epsilon, or if you like, in put epsilon for epsilon sub b. So this will be epsilon sub b over epsilon 0. Right. And all these are positive constant, f sub j, a constant, positive. This is square, everything constant. So the e plus 1, so this ratio will be greater than 1. That's the general property. Okay, so that one limit. Now, once we have that, we can now look at also the imaginary part. Obviously, this is real. It means that if all the omega sub j's are positive and non-zero, then omega sub, this is I should actually say that this is the real part, because this is real, so that doesn't matter. The omega goes to zero, epsilon is real because this is a real number. Okay, so it also means that epsilon I, the imaginary part of epsilon, and that would be zero. So we start with zero. And omega goes to zero. Now we look at how this function will move with finite but small omega. Okay. And now if the frequency actually is collision actually is small, then the gamma sub j, all the gamma sub j's are small. And the real part we can look at just ignoring all this omega, all these gamma sub j at first, and then look at what happened if you increase omega from zero. And you see that all the denominators decrease, right? Because you subtract the omega square. But you're summing all the terms, and each terms are increasing. So the total term is also, total value is also. So you start with some increasing tendency. Okay. So that's the real part. But then obviously when you talk about the imaginary part, you cannot set all the gamma sub j to zero. In fact, you can now look at the imaginary part by, like, take the magnitude of the denominator and multiply by its complex conjugate, right? And then the complex conjugate will now have positive imaginary part. And this has an negative imaginary part because the gamma sub j's are all assumed to be positive because they are damping. If it is negative, it becomes not damping, it actually grows the wave. Okay. And then the complex conjugate will be positive. So we have a positive imaginary part. And for small omega, you get this term. And then the rest is positive. So times f sub j, the imaginary part times f sub j divided by omega sub j squared. These are all positive. So the imaginary part will become positive. We start with zero, then becomes positive. Okay, so that's some kind of tendency. Okay, so that without knowing all the details, just look at the mathematical characteristic of this function. Right. So far so good, right? So, yeah. Now, of course, this consideration will need to be modified for finite omega. But in particular, when omega is large enough that you cannot ignore the gamma sub j. In particular, when the omega is large enough such that these two cancel, at least for the first one, is basically It depends on how you label that. You can sum over 0 to infinity or 0 to n, number of different kind of atom. Or, but let's see, Jackson didn't have to. That's a, if you start with 1, then so reserve omegas of 0 to the other cases. But so if you have somewhere along the line, you hit the lowest intrinsic frequency, so omegas of 1, and then might have more because you have different kind of molecules. Omegas of 2, omegas of 3, and so on. Omegas of 1, omegas of 2, omegas of 3, and so on. Right. And what happened is that at exactly, so you can look at exactly omega equals omega sub 1, then the denominator becomes totally imaginary. Right? This is totally imaginary, and then it would be also the largest one because we assume gamma is small. When omega equals omega sub j, this is also small, so the denominator will be very small. But that term will dominate over the whole summation. So this is the most dominant term, and then it's purely imaginary. So the real part will be 1 plus the rest, which is assumed to be small. So at omega over around omega sub 1. So this curve will at first it increase, but then it will get close to 1. It's not exactly 1 because we ignore other terms. Right? We have omega sub 2, omega sub 3, all that. But assuming those are far away from omega sub 1, so the denominator will be large for those terms, and then the contribution will be small. So only the omega sub 1 term, the j equals 1 term dominate. But this is purely imaginary. So you get back 1, so it's close to 1. You get down close to, right. On the other hand, the imaginary part now, when omega equals to omega sub j, this is purely imaginary, and then it's large because gamma sub j is assumed to be small, so it will get close to the maximum. It's not exactly the maximum. Again, there are imaginary part over other j term also, but those are small. You will get to some kind of maximum. Actually, only get to maximum when you get, because when gamma sub j is small, the peak is kind of narrow. Okay, and then once you go past it, it go to small value. Okay, and now obviously that when you get past omega sub 1, then other term becomes important again, and now when you get closer to omega sub 2, and omega is starting to subtract from omega sub 2 more, then the real part becomes I mean, this is decreasing, but then the other contribution becomes large and make it go back up again. So it's decrease and then it increase, and then this consideration again when omega is close to omega sub 2, then you have this similar consideration. This real part get close to 1, and the imaginary part increase, and then you can, and so on. So all these you can say is repeat itself. So you have a few peaks in Jackson got a few of these, right? And I'm not, I mean, Jackson schematic maybe a little bit. Okay. All right. So all these resonant frequency omega sub j, and the behavior is like that. And what we see is that omega sub I, the emerging part is mostly small over the range of frequency, except when we get close to this intrinsic oscillation frequency, or this omega sub j. When you get close to omega sub j, and then the omega sub the imaginary part get larger. So you have a sharp peak at this frequency. And then whenever
or will the damping increase?
Yeah, of course, this omega sub epsilon sub I represent damping. It's due to the gamma. Okay, we'll see what y represent damping in a moment. Okay, we'll just look at the epsilon first. Epsilon sub I is at a sharp peak at this frequency, and it will represent damping. In a moment we should show that. Okay, and then around this frequency also, outside this range, the epsilon, the real part actually increasing. Jackson's figure is maybe better than this because this peak is sharp, so this increase over a larger range, sharply decrease, and then go back up. Jackson's graph is a little bit better than so only over a small width, then the real part actually decrease. So there's a name for that. When the epsilon is positive, then this is this normal, what we call the normal dispersion. And when the real part actually decrease with frequency, this is called anomalous. To say anomalous dispersion. Yeah, that's when the omega part is important when you have a peak. So you keep this repeatedly until you go through all the omega sub j. Okay, so these are the reason why Jackson has this pot over there doing this kind of property. And the final limit is when I'm actually skipping over to part D when we discuss that. So let's while we are talking about these figures, finish out all the limit before we talk about the absorption. So as omega goes to infinity, that is passing all this j, right? Then the omega is larger over the denominator. All the j term omegas are larger, and so the denominator is mostly negative, and mostly negative in real part because there's one omega, two omega squared here. There's only one omega, and gammas of j's are small, right? So omega are larger, so you can actually ignore this term also when in the limit of omega goes to infinity, and it's negative. So all the terms are negative. Okay, so you can actually take in this case the denominator does not depends on j anymore, so you can take that out. So omega goes to infinity. It tends to 1. Now everything is negatives and minus n e squared. As the sum is only over f sub j, which will give you a z number of charges, electron charges, and then divided by epsilon 0 m omega square. Okay, so that's the limit. So, and then it's smaller than 1 because you're minus that. So you're minus, but it's smaller than 1, but tends to 1 as omega goes to infinity. Because when omega is large, then the whole thing is small. So at large limit goes to tends to 1. And obviously the imaginary part tends to 0. Okay, so that's the behavior. And this coefficient in front of in front of this 1 over omega squared term is we can define that as what we call the partial frequency t squared, because it obviously has the dimension of frequency, and so omega t squared is defined as n z e squared over epsilon c. That is equation 7.62. And this is the epsilon is mainly real. It's close to 1, a little less than 1. Okay, so we can come back to talk about the dispersion relation a little bit later. But that's just the behavior of this epsilon function as a function of omega. Okay. All right. Is that okay for the whole picture? Okay. So now we are seeing that sometimes epsilon can be epsilon can be compact and epsilon I can be large when you're getting close to these oscillatory frequency. And now we can look at what it means by compact dielectric constant. And we go back to the dispersion relation because of that's what we derived before. So it's still the same, still where the k square is equals to mu epsilon times omega square. Omega is real, and assuming mu is real for the time being, or you can say it's of 0 to make it near vacuum. You just ignore all the complex complex characteristic in the permeability. Assume it's very close to the vacuum values with mu. But then epsilon is complex, at least sometimes when it's omega is close to this omega sub j. Okay, and if this is complex, we can write it as alpha I. But this frequency has a real part and imaginary part. Now, when k squared equals to that, the solution for k is actually k become compact. So otherwise, it will not get to this either purely real or purely imaginary. You will not get this behavior. So k must have a real part and imaginary part. Okay, and you substitute that into here, you get the real part is k squared and then minus kr squared minus ki. And the imaginary part is 2i kr k sub r k sub I. Right. So that is k squared, and so that equals to this one. Okay, that means there are two equations actually, because you have real part and imaginary part. They need to satisfy separately. So the real part is kr squared minus ki squared equals epsilon sub r omega squared. So that is the usual one, except that now this is not the total omega, total epsilon, just the real part of epsilon, right? And then the imaginary part equation is 2i. Actually, you can forget about I because cancel with the I here. Case of R equals to mu epsilon sub r omega squared. Okay, so that's two equation. This is simultaneous equation, and in principle, obviously, you can see that you can solve like ki in terms of k sub r, and then substitute into here and get the quadratic equation of k sub r squared. So the k sub r squared. So this k sub r to the fourth power, second power, 0 power. That's still a quadratic equation. So that can be solved easily. Like
Thus, magnetic permeability doesn't have an imaginary term.
yeah, that's what Jackson using. Jackson actually use c squared, so basically assuming this is mu sub 0. You can assume there are many medium mu is very close to mu sub 0 anyway. The deviation is very small. Okay, so whether it's imaginary or real doesn't matter. Okay. And actually Jackson's equation 7.54 is exactly the equation, except that Jackson using beta as the case of R and alpha as the case of Y. That doesn't matter. And then he used C squared. C squared is 1 over epsilon 0, omega 0. So that if you use that, you recover Jackson. Okay, so that basically is that you can it's solvable, but in the case that the epsilon I is small, so mostly it's small. Even when it has a peak, the peak is still a small number because it's the square of this, the magnitude of this, and then multiplied by complex conjugate. Complex conjugate still has the imaginary positive of the gamma sub j, unless exactly this is equals to that. That is that make it large. If it is small, so if epsilon is actually small, epsilon sub I is small, then you can say if epsilon. The case of I is mostly small, so you can say roughly speaking, case approximately. So this will be just like the non-dispersive, not non when the case that we talked about, we assume everything is real, then you get this equation, except that this will be the total k, this will be the total epsilon. So, and then the case of I, you can solve this equation. Right. View, okay, and the square, and then divided by case of R2, case of R. Case of R is the square root of this one. Square root of and omega is a cancel. Okay, so approximately. Okay, so that would be I think it's actually just writing somewhere in I mean after equation 7.55. Right. So you can solve for that but this one is well anyway these are just approximation. This I mean if the condition is right, you can use that. The condition is in I is small. And but otherwise you can still solve for that. Exactly. Okay, so that's the reason why K has an imaginary part. And now we can look at the what the meanings of imaginary K, because let's go. Okay, still have space here. So usually we have to consider just one dimension propagation using one's IKX. Right? With the IKX, you have the minus I omega t, but we talk about the spatial property now. So this is equals to e to I into R plus I into I times X. Right? Now that becomes e to the I into R X. And the minus into I times X because I times I is minus 1. Okay. So this is the first factor is still oscillatory. I mean, if you like, you can separate into two exponential functions, right? It's just the same. So the first factor is still oscillatory, it's just sine and cosine, right? But then the second one is exponential function, and it's decreasing in x in positive x, obviously in going to negative x, it will be going, but then the wave is assumed to be propagating in x with a positive case of r and positive omega, because you have a minus I theta. Right? So propagate in the propagation direction is decreased. So this means the wave is absorbed by the medium. Okay, so this that so case of I with a positive case of I represented absorption, and this case of I is mainly due to this imaginary part of absence of I. Okay, so you have the imaginary part in the dielectric constant, you get the imaginary wave wave number, and the wave number actually represents the decrease, exponential decrease of the wave amplitude, and also the obviously the power also, and that represent absorption of the wave power. It's okay. So this is the physics behind the imaginary part of the epsilon. Okay, and the final remark is that we in the total internal reflection, we actually consider another situation where k is k r vector plus I k I vector, right? And we also work out what this means for this case, and this is not this is different from this case. This is the vector is there's an imaginary part in the vector, but the wave number itself is real. So this in this case, in the total internal reflection, that actually has no absorption. It just means the wave is reflected back. So in this case, this k is in the this is actually in the upper region. So you have a k that is imaginary. So there's no wave power going up. The wave power actually decreases with this is in this case in the z direction. Okay, and we also show that total power is reflected back from the incident wave, so reflected to the direction of incident. And then this is 100% reflected. There's no absorption. There's no power going through. And the structure, mathematical structure is different. This one is the wave number has this one is the you have an imaginary vector in the total wave vector. Okay, it's okay. So don't confuse these two cases. Is it clear enough? I think what we have we did something similar substitution, and we show that these two vectors must be perpendicular to each other. So the propagation direction is in the case of R, but then the case of I is the decreasing direction, and these two are perpendicular to each other. Okay. In our case, in the total internal reflection, this case of R is along this is X direction. This is case of R, and then the case of I is Z direction. Right? So they are perpendicular. Okay. Now finally, I think I actually not finally we discuss part of part B, but not totally. In we go to part C. Now with the case in here, we all assume that all the omega sub j's are non-zero, but in fact, there's a case that this may not be true. That's a situation when you not only have the bounded molecule, the medium, and you can also have some free electron. When the frequency goes to small, for free electron, you don't have the intrinsic oscillatory frequency. It might have a damping, but damping is due to the free electron actually collide with molecules, and there's a resistance or resistivity or or conductivity in the inverse sense. So there's a damping for free electron also, but no, there's no intrinsic frequency, so you can say that that represents a J equals 0 terms. If omega sub 0 is 0, okay, so that represents free electrons. So in that case, you need to, this is the sum over 1 to whatever the number of atom in the molecule. But then you have the 0 frequency term represent free electrons, so that is, you still have a, let's see, still have this N, because everything is still, you just take the J equals 0 term. So you have the F sub 0, and omega sub 0 is 0. Just minus omega square minus I omega gamma sub 0. Okay. So basically now I should say this is this is a ratio. This is so this part you still have a numbers that look like that, but then it's not the total one, because the total one actually becomes very large when omega goes to 0. That actually is singular, so actually goes to infinity, whole thing, right? So this epsilon over epsilon c, this epsilon b over epsilon c plus this part. Okay, and so that's due to a free electron. Then you can look at another way to figure out how you get to something like that, and with this is low frequency, so we go back to the equation that we worked in the later part in the chapter 5, the so-called quasi static, basically just a low frequency time dependent situation. In that case, you have well, it is just the free current density J, and you ignore the partial D partial T term. Right? That is and that is given by sigma E. Right? There's a conductivity. Right? In fact, actually, you can add the part, because we are talking about wave. This is sigma E, and now D is related to E by roughly epsilon B, because this is low frequency, and then partial T becomes minus I, and then you have the epsilon B times E. Right. And so you can all combine the two, becomes a sigma minus I T E minus omega. Okay, so that is the so when you combine with other Maxwell equation, goes through the same process. You divide the dispersion relation, and that in that dispersion that you are getting, you say that this is equal to minus I epsilon. That depends on omega becomes E. Right. This epsilon is what we've been talking about. This is what is coming from. Now we look at this one, so we can say that for this case, epsilon omega is equals, we just compare this with that, divided by minus I over here. So, so minus I cancel with that. So you have epsilon b, and then you have the sigma. I think yeah, we have the epsilon b, and then this one you divided by minus I becomes plus I sigma terms divided by omega. So that is that would be this epsilon, right? And now you can compare with what we had here. So you have epsilon b, and so the rest is very similar. So basically, when you are omega, that is very small, you can ignore this part. So you have a minus I in the denominator, which becomes a plus I in the numerator. So you have I, and then divided by omega. So everything else will combine to this sigma. So NE squared divided by epsilon 0 n. Actually, cancel this. This doesn't have epsilon 0 because this is what divided by epsilon 0. So NE squared just which implies sigma equals to NE squared f sub 0 and then m gamma sub 0. Okay, with that, if you compare this with this consideration, so the conductivity take the part of the yes epsilon this gamma sub 0, but in the inverse sense, these are just the property the fraction of free electron in over this density. Okay, and the rest is just make it dimensional.
Here, 1 to n signifies the number of atoms in that molecule, right? So what does 0 signify?
So you basically you have molecules that density of molecules and the total original total charge is z. So you have nc here. So you have the j so equals 1 to n different kind of atom. Each one have a f sub j z. The sum of f sub j z will give you z, or sum of f sub j give you z. But then now you take one of them out and call it free electron. So it's not bounded with the molecule. Also, you have a background of electrons that are going over. And the fraction of this electron is f sub 0. Okay, and you still have bounded charges molecules. The molecule becomes a somewhat positively charges, but you have a background C of electron. Okay, but the S still add up to the Z. So have sum over F sub J from 0 to N. Still you get this capital N. Okay, so that's just a model to just accounting all the charges this value. Okay, so that would be a model for the at least comparing the model of free electron to this conductivity that we just assume this empirical law between current density of electron, electric field current density, Okay, so that was this part. And well, on the other hand, of course, you can use this Ampere's law with the conductivity and combine with other Maxwell equation, the Faraday's law, and then divergence law, and divide the wave equation. You'll get exactly this the dispersion relation with this epsilon out, with this epsilon. Okay, and that will be the homework problem. The homework problem will have a ask you to divide that and with the given conductivity. Okay. Now the final part is part B with the we already written this high frequency limit. It's we have written down the dispersion relations of epsilon. Epsilon sub 0 is 1 minus approximately p squared over omega squared. So that is high frequency limit, and omega p is what we call the partial frequency. So the dispersion relation is like that, and that actually what we call the if you take this ratio, actually it's the what we call the refractive index, n, or equals to n is c squared. It's the phase velocity, which is omega over k, and then the ratio between the speed of light and the phase velocity. This is actually it's the square of n squared. Yeah, we define this. We define the refractive index with just this, the ratio of the speed. So this is n squared, right? So this is so that's the dispersion relation, and now you can solve for the k. So k would be equals to just multiply omega squared minus omega t squared, and take the square root and divide by c. Right, so t squared. So that's that we can solve. So either way, so from you can solve k as a function of omega, or omega as a function of k. Obviously, omega as a function of k is easy, even easier. Is omega. It's just square root of c squared k squared plus omega t squared. You can, in this limit, you can solve for the dispersion relation, either expressing k as a function of k. But, either way, that allows you to do some other calculation, which we haven't talked about that yet. And later on, I think it's in section 7.8. Yeah, 7.8. We'll talk about the group velocity with this function to do we calculated this group velocity. So basic group velocity would be the d omega dk in this case. That this kind of dispersion relation, you can do the derivative quite easily. And then Jackson have this, some of these qualitative discussion of absorption, especially the absorption of the air. So that is kind of interesting. So later on, we'll actually have a theorem to show that for any epsilon, we must have some imaginary part. So there must be some absorption somewhere over the whole range of frequencies. So you cannot have a medium that is have absolutely no absorption over any frequency, except the vacuum. Vacuum is like that, vacuum, no absorption. But other than vacuum, there must be some absorption. And the Jackson has this interesting discussion, then you can look at that. The main idea is that for actually this is not this is actually for liquid water. It's essentially the air also, because air has a water vapor, water molecules also. And the interesting part is that it has just a very narrow range, that it doesn't have, or the absorption is very weak. Other than that, all have a very strong absorption. So that's kind of interesting, and that window is so-called the visible light. So that's the reason why you can see. Otherwise, you cannot see anything. So it's because of the absorption over the air, coming over the air, that everything is absorbed, and you cannot see anything except through this window visible. Or the other way around, because it's not absorbed, so we can see. So therefore, it's visible. And so that's one model